Here it is. I'm about to go to a conference this weekend, and I'll meet people who are still studying this number, right? That number called Carmichael number. All right, what does it say? Is about that n has the property that no matter what a you raise to the nth power, you get that one back, right? So I forgot. It's Carmichael number is the one number that is not a prime, but it has this property. So it has to be, and it's called um, and and not a prime. Yeah, composite number that has this property. What did I call before? Pseudo prime, right? But it's really this number called Michael number. And so I'm going to explain why this one 3, 11, 17 has that property. And then once you understand, oh, all I need is this, I'm going to go in and find this one and again and more in the computer just to go out there and just find this property. All right, so let me explain why this is true. Already it's a large number, right? 3 times 11 times 17. You want to establish the product. Um, what is a property like that? What's your strategy? It's powers out. All right, that's the key. There's no computer. Powers out, completely out. Wi-Fi's dead. It's another second Irma came, whatever, something like that. Chinese remainder theorem. Thank you. That's it. Chinese remainder theorem. Let's do that. Here I'm going to explain. Z 3 times 11 times 17. This is the object, right? We want property right in that world. But this is just too much. What do? Z mod 3, right? Z mod 11 and Z mod 17. I lost one there. 17. Okay. So we have a to the n. That n is that number. 3 times 11 times 17, right? And we want to see if this is congruent to a or equal to a in this world there, right? So what do? We send that down the way, right? We have a to the n. We have a to the n. A to the n, correct? And what are we going to do? We're going to show in mod 3 these guys are congruent to a, right? We're going to show this guy's congruent to a in mod 11, right? We're going to show that it's congruent to mod a11. We're going to do that. I'm not saying that it is easy to see that. We're going to do that. 11, 17, piece of cake. We can do it, right? But now, what is the preimage of this one? A came from A. A does it, right? So there's two elements, a to the n, mapped down to this guy, right? But that's the same as a, right? But that come from a. In what scenario can you conclude these two must be equal to each other? Bijective property of a Chinese remainder theorem map. No two elements go to the different element go to the same. They must be the same element in the first place. So you're asked to show this is equal, that's equal, congruent, that's equal. That establishes these two are equal, right? Let's go and try Z mod 3. So that then you were asked to show a to the what? 3 times 11 times 7, right? This is equal congruent to a mod 3. That's what you're asked to prove. Do you think you can do it? One of the homework problem, right? If the power is this large, you can knock down by what number? Multiple of 2, not 3. That was the harder way, remember? How about here? Multiples of 10. Here, multiples of 16. They all become trivial. Right? So what is the Fermat's little theorem here? A to the second is 1, right? So if you pull out all the even numbers out of it, that's going to be just 1. It disappeared, right? Is that odd number here? That's an odd number, right? So if you divide by 2, you're left with 1, right? So here is it's congruent to 2 times q plus 1. That's for sure, right? But what is a to the second? A to the second is 1. Therefore, is a. That makes sense? Okay. Let's try 11. That's your last exercise. Is that number 3? Number 3 or 4? 3. Show that a to the 3 times 11 times 17. It was 17 before. It doesn't matter. It's an odd number, so it's the same. 17 is congruent to a mod 10. Right? Mod 11, I'm sorry. Yeah. Yeah, that was weird. Yeah, that was. But you play with 10 in the exponent level, right? Anything that's multiple of 10 will kind of disappear. See, anything multiple of 2 is just 1 blob, proof. Can you do that for me? What is it? 3 times 11 times 17? 561. That's what it was. Yeah. That part I gave you. 561. This comes free. All right, how was it? Exponent of 561. Anytime the multiple of 10 will disappear. So I organize like the 10 times 56, the remainder 1. Right? So organize like this, a to the 10. Fermat's-Little theorem was 1. You're left with just a to the first. That's what we wanted to prove. So if you divide 3, 11, and 17 by 16, no matter what is the remainder supposed to be in this part in here? If this is true, the remainder is supposed to be 1 again, right? So that you're left with a. Fair enough? So you show all that. These are all congruent to a. Then its preimage is simply just a. But because it's injective map, Chinese remainder theorem, these two must be in the same element. A to the n is congruent to a. If you think about how much calculations are saved here, it's just pretty impressive. All right? What are they called? Carmichael number. You go out and try to find another triple of prime numbers have this mutual property. When they reduce each other, it becomes 1, and you have another Carmichael numbers. N equals 1. That's right. All right. 1992. 3 people in the University of Georgia. Three number theory. Andrew Granville, Carl Pomerance, and Alford, who passed away and recently, proved there are infinitely many Carmichael numbers. It was a big deal. The technique and all that thing was amazing. It's very, very difficult, but it was right up there in 4 hours drive from here. It was proved. There was quite a celebration that they finally proved it. University of Georgia. Yes. They're all gone. Carl Pomerance is Dartmouth, and Andrew Granville in Montreal. Alpha passed away. But I was there when Carl Pomerance and Andrew Granville, all under that amazing activities going on, and they have amazing group of number theorists, and I was privileged to study under them. Yeah. Carmichael numbers.